Welcome to the 7th Practicals. Today we again have a special guest, Tanya.
Hi.
She will introduce or recap operator overloading at the very beginning. So as you might have guessed, we'll talk about operator overloading today. We'll have many examples. We'll again reintroduce some classes that we already wrote in the practicals and implement operator overloading for them, especially for the assignment operator. And then at the end, finish the lambda functions that we started last time.
Okay, so then let's get started with operator overloading. So just to recap really quick what operator overloading was. It basically means that we define a custom operator behavior for a non-native data type. So not something like integer or floats or any other native data types that we already have, but something that we define ourselves. And basically most operators can be overloaded. I've linked you the list again to the CPP reference page for that. So yep. So just to show it here really quick, we have a very simple example with two integers, and if we add these together and print them, we get the result 3, because 1 plus 2 equals 3. C++ knows how to deal with that. But if we have something like a custom class called object, with a private element that's also an integer called element, and we just try to do object 1 plus object 2, C++ is going to scream at us because it doesn't know what to do if it has an object of type object together with another object of type object. So it also says here that the operand types are object and object. So that's the behavior that we want to define with operator overloading. What actually happens when we have something like this? So to do that, we're going to look at a time class, which defines timestamps that consist of hours, minutes, and seconds. And our goal is to be able to add them up, increment them, compare them, and also print them. Right, so let's get started over here. So I've already made a bit of a skeleton class for that, so we can see this is just a simple time class with 3 integers, second, minute, hour. We have a small normalized function, so we can prevent seconds or minutes from going over 60. And we have a function that converts our time to seconds, which will be useful later on. And we have a simple constructor that just assigns our values and getters for our attributes. So how we want to start with overloading an operator is, let's start with the plus operator. So how we have to define the function header is we have to use the operator keyword and then the operator that we want to overload. So in this case, that's a plus operator. And if we think of, if we say we have a time object time1, for example, let's do 16 o'clock. And just a simple time object 2, which is just 3 o'clock, 2 minutes, 1 second.
Yeah, so note that here we have the hours in the last place.
Yeah, those are switched. Yeah, that's because we take seconds first here, right? So don't be confused by that. So basically what we want to do is we want to do something like time 1 plus time 2. And we want that to work for us so that we can, for example, create a time 3 object with like the result of the addition of these two. Of course, that doesn't work yet, but that's basically what we're trying to achieve. So we can overload operators in different scopes. We can do it as member functions. We can also do it outside of a class. We're going to start by doing this inside of the class as a member function. So basically what we want is we want to get a time object returned from this equation here, which will then be the time 3 object. So we want to return a time object. And one thing that's also interesting is you would think that we need 2 parameters, right? Since we're adding up 2 values. But if we're defining it as a member function, you can think of it as basically doing something like time 1 plus time 2 is the same as doing time 1 dot operator plus with the time 2 object. So it's kind of like a fancy function call if you think about it. So that means if we're doing it inside the class, we actually only need one parameter. And since in an addition, we don't want to change time 1 or time 2, we just want to have something new returned, we can also define that as a constant. So we're going to do a constant time reference that we'll just call other, just so we know that this is the other side, so to say. So that's the function header we have. So let's implement that in the CPP file. So to do that, we need our scoping because we're in the class, right? And then, as we said, we want to return an object that is just the result of adding the time 1 and time 2 together. So we'll create a result object. We'll just initialize that with zeros. And then all we have to do is define the attributes of our result that we have here. So result.hour would be the hour of the object we're currently in, plus the other object, the hour attribute of that. And basically we'll do that for the minutes and seconds as well. Exactly, and at the end, we want to return the result. As simple as that, really. So if we scroll a little down, we'll also see that our squiggly line here has disappeared because we have now implemented our operator. So now, I'll just put this away. Let's see if that worked. If we just print our time 3 object, so we'll start with, we'll just try to format that already as a timestamp, and we'll just use our getters to get our values. And add a new line at the end so we can see something. And if we now just compile that and exit, what did I forget? Did I forget something? Did I forget something?
Oh, you need to save.
Oh my God, I forgot to save. Classic beginner mistake. Whoops. It happens to the best of us. Exactly, so now we have, since we had 16 o'clock here, and we had 3 o'clock, 2 minutes, 1 second, now we have 16 plus 3, 19 hours, 2 minutes, 1 second. So our plus operator works. Now, what if we want to also define that we don't actually add up 2 time objects with each other, but we just add, for example, 50 seconds to this one? Well, that again doesn't work because we've only defined what our class is supposed to do with the plus operator if there's a second time object, but we haven't defined it for an integer. So now we can also do that, and to make it more interesting, let's do that outside of the scope of the class. So we again need our time as a return value. We want the operator plus. Now, what do you think is something we have to do differently if we're not inside the class anymore? Does anyone? Yeah? We don't need to scope it. That's one thing, yeah. But in terms of parameters, yes, if we keep it in global scope, that is true. But what I actually just wanted to say is that we need to also define the second part here, because here we only had one time object, even though we added up 2 time objects, right? And here we're adding up a time object and an integer, and we can't just write the integer because we're not inside the class anymore, so we're not calling it on an object itself. And that's why we also need a constant time reference here at the beginning, which we'll just call time. And we'll do constant integer reference, which are our seconds. And now there is a keyword you learned last week with how we can actually allow this function to access private attributes and just private member functions and all of that in the class. Does anyone remember what that is? It was a C++ keyword. I heard it already? Yeah, friend, exactly. So just to repeat that real quick. Friend allows functions to access private and protected members. So we have, here's just a small example. We have a class object again with an element. And we have this global print element function that just prints the element. And we can just take this function header, put it in the class, put friend in front of it, and then we can still access this private element. And it's just going to print us the value we set the element to at the start. So that's basically what we want to do now as well. If we go back here, we will just take this whole thing. Yeah?
We already put the function, the method in the class, and why do we need friend keyword? Because it can access the members if it's in the class.
Yeah, but it's not the same function. Now we're doing a plus operator with a time object and an integer. Before we did it with 2 time objects. That's a different function.
Yeah, okay, I can ask for the example of this.
I mean, yeah, you could also just put it in the class, but for completion's sake, we're also showing you how to add it with friend if you put it into global scope. So we'll put that here. So now we just have friend and our operator with our seconds. Now we, of course, still have to define that again over here. If we go back to the CPP file, oh wait, that's in global scope. Whoops. All right, that's done here. So we don't need scoping since we're in global scope. So now we want to, again, have our result that we had before. Now we can basically almost exactly copy this, just that we're not adding everything up, but just the seconds. So we have now our result.hour should be time.hour, result.minute should be time.minute, and result.second should be time.second plus hour seconds. And we just return the result again. So now if we compile this again and execute it, we should get 16 o'clock and 50 seconds. Did I save? I did not save again. Exactly, so we have 16 o'clock and 50 seconds. So it's a bit of a drag to print it like this, though, because we have to use the getters and we have to define all of this ourselves. If you want to use this in multiple places, we have to write the entire thing every single time. So let's make that a bit simpler by overriding the output operator, which is this one. So the brackets we always use if you want to print something to see out. There's a bit of special stuff with this one, though, because we are still writing into an output stream, so to say. And the reason why we can put, for example, this plus operator in the time class is because we're adding up a time object with another time object. So the left-hand side, so to say, of that equation is of the time class. But in order to do that, we would have to basically put our overloaded operator for that into the output stream class, which is a standard library, and we kind of don't want to do that. So what we're doing here is we will override it in global scope, and we will pass it, oh, I forgot the std. We will pass it an output stream reference, which is really important because we cannot copy the output stream. So we have to use a reference here. We'll just call that stream. And we once again want to use a constant time reference called time. And again, the reason why we can't make this constant, for example, is because we're actively writing into it. So we want to change it. So that's why we can't put a constant here, for example. And what we want to return is once again an output stream. But we have to also make this a reference. So something like, let's say, if we do something like time 1, time 2, so we chain these together. In order for that to work, we have to use a reference here. Otherwise, we wouldn't already have the changes in the output stream for the second call to actually work. Exactly.
Yeah. So I think last time in the lecture you learned this more or less like method chaining, where you return this. This is now very similar with you returning the reference to the stream again so that we can apply this operator a second time and print many things at once.
Okay, so that's our function header done. So then we can once again switch over to our CPP file and implement that. So basically what we want to do here, we want something like time 1, time 2 like that to work, but let's keep a similar structure that we already had here. So we'll just take that. And we will write that into our stream reference that we passed as a parameter up here. And we have, of course, now we don't have time 3, but we have time.getHour, time.getMinute, and time.getSecond. Now we can also say that we want to format this a little bit nicer. So maybe you already stumbled over it in your A1 implementations or in A2 as well, but there's a class called IOmanip, where we have functions like, for example, std_setFill, which defines a character that we want just to be a filler character, basically, in the following expressions. And there's also a function called std_setW, where we can just set the width of an expression that comes after it. So this basically defines that whatever is returned from getHour has to have width 2, and if it doesn't, it gets filled with a 0. So we have a bit of padding going on there. Now we'll just put that here as well. Oops, not like that. And another time here. Right, so now that is a very long expression that we're just going to try to make a little bit more readable. Right, so this is really long, but let's check if it works for now. So now we should get our time 1 and time 2 printed. Yeah, time 3 is, oh no, we forgot to return it. We of course have to return the stream again. And we'll comment that out for now. Now, so now we have 16 o'clock, 3 o'clock, 2 minutes, 1 second, but padded with zeros and with a new line and everything. Looks really nice. But this is a bit of a drag also to write, because we at least have it in one place now, but having to do the set fill, set width, and all of that is also really tiring, and we want to keep things as short as possible. So there is this nice little feature that we've had since C++20, or not feature, more like function, called std format, which is basically printf from C making a return. Because basically what we're doing here is we can once again define a string with format specifiers and then just add afterwards what should be put into those format specifiers. So here we can just say, okay, we get our time.getHour. We'll get to the front part in a second. So we again have our getters. So we have the hour, the minute, and the second. And at the front, we now need to do our format specifier. So what we do here is we put curly brackets, colon, and then we say, hi, please fill this with zeros, make it too wide, and please print an integer. And congratulations, we now have the same format for get hour, just instead of this, it's just this. So that's a lot nicer. Now we just do the same thing 2 more times. Oh, forgot the colon. And then we also add a new line at the end. And that results in the exact same thing as before. Just that now it's a lot shorter and a lot more readable.
Does anyone have an idea why it is important here that we here write the string into the stream and not just write std cout? Yes? Yes, exactly. Because if we implement this operator like this, and we get the stream and we use this stream, then not only does this work for cout when we want to print to the console, but maybe we want to write the string representation of our object to a file. So if we open the file, then we can just use this operator to write to the file.
Okay, so now we've finished our output operator. So we have 4 more operators to go. Next one we're going to do is the plus assignment operator. Now, if you think about it for a second, in terms of how, if we have something like time 1 plus time 2, right? And then we have something like time 1 plus equals time 2. In terms of what gets modified, what's the difference between these two? And what could that mean for our return value here? Yeah?
The second one, you just sum time 1 and time 2 and reassign the result to time 1. So that is different from the line above that.
Exactly. And since we reassign the result to our time 1, we actually have to put a reference here. Because here we worked with a copy, right? That we just returned a new object, so to say. But here we have to actually work with a reference. But otherwise, this is very similar again. We, once again, have a constant time reference that we shall call other. And we'll implement that. We are, again, in the class scope here. So before we were in the global scope, now we are inside the class again. So we will scroll up here and put that here. Right, now here we can just do, again, our hour plus equals other.hour. That's not the same plus equal we're overriding. Do mind that, because hour, the hour attribute is an integer, so I'm just using plus equals here because it's just shorter, but you don't have to. You can just also say hour plus hour, hour equals hour plus other hour, just so that's clear. So we will just do that again. And now we have to return the object we're working on right now. You also learned about that last week, how you can, that was also a keyword, how you can access an object itself inside of class methods. Yeah? This, exactly. So just real quick, as a recap, this as a keyword, this as a keyword is a pointer to the current object. It's only available inside class methods, and if you dereference it, you get to the object itself, because this itself is a pointer. So that also means we can't do it like this. I mean, we can't do this like that, but we have to dereference it. Yeah, that. If you're trying to talk about that keyword, that's really confusing, but okay. So we just returned this down here. And if we, for example, just do, you know what, let's combine these. Let's do time1 plus equals time2. So we have two operators at work here. We're printing with our overloaded assignment operator, and we're using the plus assignment operator. That should result again in our 19 o'clock, 2 minutes, 1 second, best case scenario. Yep, so that works once more. Now, what we also want to overload is the plus plus operator. If you, no, all of you have used this before, but you can do time plus plus, but you can also do plus plus time. And there is a distinct difference in these two, which we'll just also recap real quick. Pre-post increment operator, you guys can read that, right? Okay, that's big enough. So we have an integer pre, an integer post. They're both set to 0. The pre is increased with the pre-increment, and the post is increased with the post-increment. So what do you think the result of that line is going to be if you print it? 1, 0. Who thinks something else? 0, 1. Mm-hmm. Any other guesses? I mean, we only have 4 options, but could be 1, 1, maybe. Let's see. So if we run that, we have 1, 0. Now, why do we have 1, 0? Because the pre-increment operator immediately increases our value before we use it here, and we already get the updated value. With the post-increment operator, we also increase the value, but for that call right there, we're still using the old one, and only after that we're using the new one. Like the next time we use it, it's going to be the one as we see down here. And that does make a huge difference when you want to overload these two, because that does make a difference. So let's start by overloading the pre-increment operator. Now, since we said we already immediately want to assign that, who thinks we need a reference here? And who thinks we don't need a reference here as a return value? Who thinks reference? Hands up. Who thinks no reference? Okay. We do need a reference. And we shall see in a second why. So this is how the function header looks then. And we'll go over here again.
Yeah, so this is now the pre-increment operator, pre like before, so when we write plus plus some variable.
So we just increase our seconds because, not sure if I said that before, but with the increment operator, we only want to increase the seconds. We'll just define it like that for now. So that increases our seconds. And then, once again, we can immediately return our object with this. That's the pre-increment operator. Now, the post-increment operator is where it gets interesting, because here, we do not use a reference for a good reason. We again write operator plus plus, and this is also an important distinction between the two, because the way we we overload our operators is with the operator keyword and the operator behind it. We can't really make a distinction with this type of syntax of which one's the one we used before and after the expression. So how we handle that difference is that the pre-increment operator just does not take any perimeter, but the post-increment operator kind of takes this dummy perimeter, just so we know, by the way, this is the post-increment one. This isn't the pre-increment one.
Yeah, so this integer, you shouldn't use it. It's just some kind of hack C++ uses. So it can distinguish those two operators because, yeah, I mean, they are the same symbol. How else would it distinguish those two functions?
So let's overwrite overload this one as well, not overwrite, that would be bad. All right. So with this one, because we already mentioned, as we saw here before, we want to use our old value one more time, but also increment the one we had. So what we do here is we actually create a temporary time object, which we can also conveniently just assign with this in that case. Do be careful the way I'm doing this here. If you were dealing with pointers and stuff, you know, shallow copy, deep copy, be careful with that one. But since we're only dealing with integer stack values here, that's fine. So this does work. We again do our plus plus second, like we did before. But instead of returning this, like we did before, we return the temporary object. So in the background, we're still increasing the seconds, basically. But we are one more time returning the value we had before increasing it.
Yeah, so maybe now the example we had before with the integers is a bit more clear now that you can see how these operators work. The post increment operator really just gives you the same value back, but as a temporary value, as a copy, but then actually increases the value that is our variable.
Okay, so let's try those out. So let's do something like, let's do time 1 plus plus, but we'll do plus plus time 2. And then we'll just put those away, just so we see the difference one more time. We now compile that. Time 1 is our 16 o'clock. Time 2 is our 3 o'clock, 2 minutes, 1 second. Oh, I forgot something. Did I forget the semicolon?
No, you still have the lines in the main that you wrote for an example.
Oh, whoopsie, right. Forgot to remove those. Right, so we have one more time 16 o'clock because we use the post increment here, but the next time we have 16 o'clock and 1 second. And with time 2, which is 3 o'clock, 2 minutes, 1 second, we immediately have the seconds increased by 1, and it stays that way. Exactly. So then we have, oh, sorry.
Can we skip the last operator?
We can do that. We
Maybe
can do that.
We can also leave this as an exercise to everyone. So we would have planned to just implement the comparison operator, but I think, yeah.
So that would be a smaller equal than, or unequal to, or whatever. Try to implement those. It's a bit easier, I would say, in terms of return value, just as an exercise. Yeah.
Yes?
The post incrementation, yeah. This one?
Yes. So the reason we need the reference in the pre-implementation is because we are actually incrementing the object that's given and then returning it. But in the post-implementation, we have a temporary object which is then incremented and then returned.
No. We were increasing the object. We're calling it. We're calling the operator on here, right? So you need to imagine basically when you say like time 2 plus plus, time 2 plus plus is like, as we said, 16 o'clock. This line here, oh wait, that's the seconds. This line here, the plus plus second, does increase that to 16 o'clock and 1 second in the background, but because we're using the post increment, we want 16 o'clock to be returned one more time. So that's why we're saving the 16 o'clock in here and returning that, but we are still increasing the object itself to 16 o'clock and 1 second. Okay.
Yeah, so sometimes you need to be careful about the difference of those two operators. Most of the time it doesn't matter, but if you use the value directly, then yeah, you need to think about this.
All right. I guess that's it from me then. And yeah, thanks for having me. And I guess we'll do a switch, right?
Yeah, very nice. So we have seen a lot of operators now, thanks to Tanja. And now we continue with probably the most important operator, with the assignment operator. And yeah, maybe we directly demonstrate it by an example. So at some point in the practicals, I think at the very beginning, we created a vector, so an STD vector on our own, which then stores integers on the heap. And yeah, we implemented some parts of it already, but there are some tasks still missing. And one of them is, of course, the assignment operator, and yeah, which is a bit tricky there. But it's also a nice opportunity to actually implement like a funny operator, which was called in the last lecture, with the array indexing. And one more open thing was there. When we index something, there's also the question what to do if we are out of the range of the vector, then we can fill this up. Okay, so let's quickly remember what we have done so far. So we had this vector class, which has some length, and the array where the actual integer values are stored. And we had already a constructor which initializes the length and creates the array on the heap. Then we also have, of course, a destructor which then deletes the array. And what happens if we have a destructor implemented? We always need to think also about the copy constructor, and we implemented it explicitly because we really need to copy the array on the heap. If we don't do that, we would work with the same memory in both objects, which would not work out. And then we had some getter for the length and the array indexing with the add method.
Yeah, but last time here we didn't know what to do, right? Because if we try to index something that is not in the vector, so out of bounds, we kind of got confused of what to do because we just wanted to return integer reference, which can be null or something. Yeah, but I think we now know better. Does anyone have an idea what we should do if we are out of bounds? Yes, exactly. Now we can use exceptions. Yeah.
Keep on talking. I need to fix that.
I think, yeah, maybe I'll implement it for you. So what do we do here? Well, let's not implement something new, just throw the exceptions that we already know from the vector, because we can do that. So here in this add method, we get the index, and if it's the same size or bigger as the length, or if it's not greater than 0, so something negative, then we just want to throw an exception to signal that there is something wrong. So I will just throw the out of range exception that we already know from the vector. Here we also need to provide the what variable. And I think this is just index out of bounds or something with the default vector. And now we also won't get a compiler warning because now the compiler sees, okay, if this if is true or false, in each case we either return or throw an exception. Before I think we got a warning because if this if is false, we didn't return anything, but the function has a return value. So we fixed it.
Okay, very nice. We also provided a main function here where we create an array of size 10. Let's directly try that out, what we have done. At 11, for example, should hopefully then produce an exception. And if we run this now, yeah, index out of bounds. Now this one fix, which was the fix which was not related to operator overloading, but now it's already done, very nice. Then maybe we stick to this function. Now the question is, can we also, instead of writing the add method here, do something like list with the brackets operator at maybe something more useful, maybe at 0. can we also achieve that? And the answer is yes, using operator overloading. How is this operator then defined? Yeah, no surprise. It also needs to return an integer reference, same as the add method.
Yeah, so what you return from this operator is up to you, of course, because yeah, it's just the return value of this expression if you access with the brackets.
But we would like to have a reference here because we would like to be able to do something like this. And if we just return an integer, then where would the 10 be assigned to? To some integer which is a return value and then vanishes. So it doesn't make sense.
I think this even would be an error then.
So we use the reference, so the 10 gets then really stored in the array. So also no surprise that as we have seen, we use the operator and then the brackets. Okay. What is the argument? An index.
Yeah, and this argument again doesn't have to be an integer, because as we've seen with the standard map, we can also use any data type to move these bracket operators to access.
So we can also specify like multiple of these operators. And the code is the same as before. Yeah, and now this should work out. Maybe remove this here. And maybe fill it at position 1, the 10 after. So we initialization of the array just initializes everything to 0. And then at position 1, we set it to 10. At position 0, we set it to 350. Let's see whether that works. So we have, oh, actually it doesn't initialize, it initializes with the position. Sorry. But at the position 0, we have 350. At position 1, we have 10. So this operator now also works. Okay, now the crucial thing. These were the funny tasks. We need to implement an assignment operator. Why is that?
And you really need to implement it, because we have a destructor, we need a copy constructor, and an assignment operator. We really need to implement it, or at least delete it.
Let's see what happens if we don't do that. So maybe we create a second vector, your list, maybe of size 20. Okay, then we have two independent lists, okay? And now maybe I want to have your list in my list. So my list equals your list. And the problem is this works now. Yeah, so if we compile this.
Yeah, so normally you would expect that if we use an operator like that, without implementing it, you would get an error like operator for those operands is not defined or something like that, as we have seen before. But this would kind of suck if we had to implement all these assignment operators for all our classes, because maybe if we just have some really dumb class, we just store some integers or something, we probably want to assign it at some point.
And now you call Tanya's class dumb because it just consists of integers. But yeah, but basically that's it. Yeah. So this is then there by default. And this is also the problem because we did not get the compilation error. So maybe we don't know. We execute it and double free. Has somebody an idea why this double free now happens? Why do we have a double free here? Is it large enough? Should increase it a bit. Maybe it's better like that. Somebody an idea?
Yeah, maybe just for clarification, the default implementation of the assignment operator is similar to the default implementation of the copy constructor. It just copies over all member variables. Or you can even think of it like a mem copy, maybe even.
Should we answer it, I think? Or, yeah? Mm-hmm. Yeah, so basically you're right. It's again like a shell or copy. So what does the assignment operator do? As you said, okay, the length, yeah, we can copy the length easily, no problem. but we also simply copy the pointer here, which means that your list and my list then have a pointer to the same underlying array. So there's just a single array where the values are stored, but both vectors point to the same array. And then at some point we will destruct your list and you will free the array. And later on I will also free my list and I free the array again, which is then freed twice. And on the other hand, at the beginning, I allocate memory for my list, and here I don't free my list before I assign it. Yeah, so basically it's very similar to the copy constructor. Now let's implement it. Assignment operator, we would like to be able to kind of chain these operators here. So we also need to return something, vector reference.
So if you chain them 3 times, like you did here before, can you write it again?
Maybe let me write write this first, and then let's call it right-hand side. This will be the signature. And if I do it like this.
Yeah, maybe now list 3 or something.
Okay, list 3.
Now, will my list have the value of your list or list 3?
So we can think about it like this. So list 3, so this will be executed first. Your list is the left side. So this is the object where the operator is called on. List 3 is the parameter, so the right-hand side. So your list will then become list 3. Okay, then list 3 is returned. No, your list becomes list 3. And since your list is list 3, your list will be returned, which is equivalent to list 3 or the content of list 3. And then your list, which was updated, is then again the parameter for the second times of the assignment operator, which is called on my list. And then my list will get the value of your list. But since you got the value of list 3, I will also have list 3 in my list. Yeah, all of them will have list 3 in the end. Now, and we need the return value to allow this chaining here.
This is just something interesting that actually with the assignment operator, you have this more or less precedence to the right instead of to the left, like with the plus operator. Because if you do something like 1 plus 2 plus 3 in C++, you would expect that something like 1 plus 2 is executed first and then plus 3. And it is like that, but with the assignment operator, it's the other way around, where you start from the left.
From the right.
From the right.
From the right. Okay, now let's implement this. And 2 steps. First, if we want to assign something to some list, we need to clean up that list. So we should do the same thing as the destructor does. So we just call delete on the content. So we delete everything which was stored in my list. And then we update to your list. So we say that the length becomes right-hand side length. And the array should be a new integer array of size length. And then we should also kind of copy the values. So maybe size t, or just keep it with an integer. We iterate until length and copy into the content of right-hand side array at I. Okay, so we clean up our array first. Then we update the length. We initialize a new memory on the heap, and then we can copy all the elements of the right-hand side array. Now let's check this. Maybe, so let's get rid of something here. I think we don't need this anymore. I would just, print array my list. Then I'll do the assignment, and again print array your list. So in the first place, my list has size 10 elements should be printed, and once we assign it, then we will again print my list, sorry, and 20 elements should be contained in my list. Let's check
You get the warning, yes.
Oh, I forgot the return value of the assignment operator. Yeah, so we return, again, the address of our object dereferenced for the chaining. Okay, and yeah, this seems to work. Okay. Mean question, do you think this always works? Or do you think that we might have forgotten something? And once I ask in this way, then the answer may be obvious. Okay, that was the cable, sorry. Okay, no. We forgot indeed something. What happens if I write, yeah? If you assign something which is not an integer, I mean, we can only assign now vectors to the vector. So this shouldn't be a problem.
Yeah, if we implement the vector for something else than an integer, then of course we would implement some weird logic with the assignment operator where we allow assigning different types.
But it would be possible. Mm-hmm. But we have one more case here. What happens if I do this? If I assign my list to my list? I mean, let's try it maybe. So there is a warning. This is nice. It looks like it worked. Can this be a problem? Probably. Yeah. So what happens? Well, my list equals my list.
Maybe you can also move the assignment up. Like,
where would you like to have it?
Yeah, something like, no.
Here?
Yeah, okay.
Now you can get rid of the other stuff, basically.
Now we have it again at the end. Move it up one.
Okay, you want something like this.
Yeah.
But it shouldn't be a problem, I think. It will still work. Maybe not. Maybe halfway. Yeah. Mm-hmm. Yeah.
So we are trying to assign read part of the memory.
Yeah, this is true, yeah. Because what happens if we do that? Okay, we will go into this operator. We'll delete the memory of my list.
Because, of course, in the assignment operator, if we assign something to the, we want to like delete the left-hand side because we now want the left-hand side to be the right-hand side.
Yeah.
Yeah.
So we always delete the array of my list, but then we also delete it of the right-hand side because it's the same object. And then, okay, the length assignment will work. We can also allocate the new array, but then we copy here the elements from the right-hand side to the left object, but it's the same object. So we basically allocated the memory here and copy from this block of memory to the block of memory. It's the same memory block. So we first deleted the values of my list, then created a new block of heap memory here, and then did some assignment there. But I mean, we could have lost all information of the array from here to here because we freed the content of our array and then later on allocated it anymore. And this is just like assigning the values to the same block of memory from the same location to the same location. This is then meaningless.
Yeah. And what I wanted to happen when you move it up is that the second allocation, that if we might get unlucky, happens at a different place than the last one was. So if we allocate a new array, then we lost all of our data if it's at a different place.
Mm-hmm. Yeah, which was also partially done here. How can we prevent this? We just check at the beginning if we are allowed to do this assignment. So basically we check if our address is different from the address of the right-hand side. Because if this is the case, then it's not the same object anymore, and we can do all the stuff in between, free the memory, allocate the new memory, everything is nice. But otherwise, in this case, we would free our memory and then allocate it again, do some assignment, which is not very meaningful. I hope this is clear. And now just to emphasize this, I mean, okay, I don't go through this anymore, but basically the problem with the copy constructor was this shallow versus deep copy problem, where we said, okay, the default copy constructor just assigns the pointers, assigns all the values, but it does not allocate a new memory in the heap, so we get maybe a double free. And either we write the explicit copy constructor or we delete it. And now exactly the same principle as also in the assignment operator. We always have this default copy assignment operator or assignment operator. Copy assignment or assignment operator is the same. Yeah, it's like two names for the same thing.
Yeah, so different from copy constructor, but copy assignment operator is the same as assignment operator.
Yeah. And so the default one, again, just copies it as we have seen and doesn't care about freeing memory, allocating memory. So again, we need to either do it explicitly, where we delete the old memory, allocate the new memory, and think about the case where we assign an object to itself. Or the alternative is, of course, we can also delete it. Yeah, so we can again write here equals delete, and then there is no implementation of it, and we cannot use it anymore, as you can see here. Yeah. So this is also an alternative. And now we come to the rule of three, and we really talked about this a lot, but for us it was only a rule of two. We always said if you have a destructor implemented, don't forget about the copy constructor, either implement it explicitly or delete it. And now also the same holds true for the assignment operator. If you have either a copy constructor written, an assignment operator written, or a destructor written, one of those three, then you need to consider all three and either implement them, all three, or delete some of them, or delete all of them. I mean, you cannot delete the destructor, but delete the copy constructor and assignment operator. But you always need to think about all three. And it is also important for the assignment. And it's a bit unfortunate that we tell you this 1 week before the deadline, but if you implement some destructor at some point in your assignment, then also delete the assignment operator, please, as well as the copy constructor.
Yeah, I think you should have already deleted the copy constructor or implemented it. But yeah, you can now, I mean, it's a quick fix. You can just delete the assignment operator if you have some class like that, because hopefully you didn't use it up until now. And if then you get the compilation error, then you had memory issues.
Yeah, so this was really important here. Okay, and do you want to implement more operators on the smartphone?
Yeah, I mean, we have next week.
And we got like 5 to 10 extra minutes to test. Lecture's a bit shorter.
Okay. Yeah, do I have some recap now? So let's look back at
on the very below.
I want to get back to our smart pointer. Because I think last week we implemented the shared pointer. Maybe just a quick recap. How does this work? We have this pointer here to a student, which is on the heap. We allocate this here. And we also have this ref count on the heap, which we allocate here. And then, if we copy our shared pointer, we actually want this shallow copy, but we want to increase our reference count. And if we destruct our shared pointer, we want to decrease the reference count. Now this is a prefix operator. So with pre-decrement operator here. So we first dereference reference count, decrement it by 1. Then if we have no more shared pointers because we're just destructing the last one, then we can delete everything on the heap and everything is fine. Maybe let's first start with the fun stuff. now we can actually override some operators to make our life easier, because this deref function was a bit weird.
So you want to dereference now the smart pointer using an operator.
Yeah. And what operator do we know? Well, there exists this, not the multiplication operator, but the dereference prefix operator. Pointer, yeah. So, which just dereferences our pointer. So this does the same as deref. We could also call deref here, but maybe it's a bit more clear like this. And we return a reference, of course, because we want to be able to do something like dereference our shared pointer and then assign some value to it. Or it's a student, but also modify it, so we want the reference.
Maybe you can see that in the main or in the print?
Yeah, we can use this in the print now. Instead of this dereference here, we can now implement this with the operator. Did we have it like at this size?
No, this will work out fine.
Yeah, we can now use the dereference operator we just implemented here.
So
So this is already nicer and a bit like the C pointers that we are used to.
Okay, but now if we would have a real smart pointer here, we could also write kind of student and then the
Arrow like this, yeah. But this does not work, and we can see, okay, now we don't see that this is not implemented, but yeah, we get an error. And actually we can also overload this error operator here. Now we actually need to return a pointer in this operator. So this operator, you get this left student here, and we need to return a pointer which is then dereferenced, and the right method or attribute is searched in this type.
But it's a bit awkward, this pointer here, I must admit.
No, not this, the pointer. Okay, so now if we use this operator on a shared pointer, instead of dereferencing the shared pointer, we are actually dereferencing the pointer that we have stored in here.
And this should now work in the print as well.
Yeah, we have no errors.
We need to switch folder. Smart pointer, I think.
And yeah, still seems to work, the print function. But maybe
can you scroll up to the class?
Sorry.
Okay, so what is interesting about this class now? So we have a destructor here, and we have a copy constructor and the constructor. So what should we do now?
Yeah, we need the assignment operator as well, because now if we create a second shared pointer, something like this, and maybe the name of the assignment operator now, okay, we do not get an error, but maybe let's check with Valgrind if we can see it. Yeah, we lost some memory though.
Yeah, so we got 2 errors again. Yeah, so something is odd here again.
Because we called it the copy assignment operator, we are copying this shared reference to this one, but we are not keeping track of the reference count. So the reference count, now we actually have one more reference than we think there is, and we have one less reference to student 2, but we did not count destroying this reference. So the student 2 thinks it just still has one reference, the shared pointer, but actually we do not have any reference to student 2 anymore.
Yeah, so basically the student 2, it points to Michi with one reference, and after the assignment, it doesn't point to Michi anymore, but we do not explicitly delete me.
Yeah.
Yeah, so this is the
Yeah, or you
problem.
can also think of it like the reference count is still 1, but we do not have any reference anymore because we just overwrote it.
And on the other hand, we should have 2 references to you because both objects point to you. Yeah, okay.
Yes, actually, I think we would get an error if we use me down here, but maybe let's just implement it. Yeah, what do we need? We return the reference like we have seen before. Then we get also a reference to the right-hand side, like this. Now, as you have demonstrated, the first thing we need to do is we need to check that we are not the exact same object as the right-hand side. And something like this. Yeah, what do we need to implement now? Well, more or less first, the same thing as in the destructor, because we need to actually decrease the reference count of the current class we're in. Because this right-hand side, we want to assign this to ourselves, so we have 1 less reference to the object we are referencing, because we're now referencing this other object. And now, if this ref count is equal to 0, then we need to do the same thing as in the destructor. We need to delete it.
Dereference the ref count in the if.
Oh yeah. This would already be a hard to debug problem because we would never free it now.
So now we kind of deleted the old object, and now we can really perform a copy.
Yeah, something like this. And one last thing that we should not forget, we actually need to increase the ref count now, the current ref count again. Now the ref count is the ref count of the right-hand side. Maybe we can make this explicit. I mean, it's the same, but yeah, we need to increase it because right now we are actually referencing this other object.
Now, if you maybe scroll down to the destructor, yeah, we had this if, we decreased it, checked it for null, and deleted it, and both appears in the assignment operator as well at the beginning. And then if we have a look on the copy constructor, in the initialization list, we assign the values of the pointer and the ref count and increase the ref count. And the same is happening also in the assignment operator.
So actually, this is just a destructor, and this is the copy constructor.
It's kind of a combination of both of them.
Yeah.
Maybe run it, but it should work, yeah, but nevertheless. Compile, and maybe with Valgrind, then that we see all the mistakes are fixed. Yeah.
Yeah. So now we didn't lose any bytes.
Okay. Yeah. So far everything clear regarding operator overloading. Or do you have any further questions?
Yeah, maybe if you didn't quite get the assignment operator for the shared pointer now, you can check again the slides from last week, think about how the shared pointer worked, and maybe try to come up with this assignment operator on your own. And then it should be pretty clear what to do.
Okay, now it's the same situation as last time. We have only a few minutes left, and we still want to talk about the Lambda functions. And I think we will conclude the Lambda functions today, but we prepared also something on top of that, so we'll see this probably next time. Yeah. Okay, maybe I will just show you the example that we did last time to demonstrate what a Lambda function is. So we prepared something like that. Okay. So again, we have our class student, as we also had in the previous example. And then we we had here a vector of students, so we're both in there. And then we said, okay, we can create now functions inside of the main function and have them as variables. So we have here this print student lambda variable, which is basically a function. Yeah? A function which takes a student, returns void, so it doesn't return anything, and it then prints something. Yeah? So it takes the name of the student and then prints the name of the student. And then we also had a function for each, like an ordinary function for each, which got the array of the students and a reference or a pointer to the function. So we can, for example, have as one parameter the student list, as the second parameter this lambda function here. And then we just iterate over the vector and execute the function for each student. Yeah, and for example, if we call for each with the vector and the print student lambda, then, okay, we would iterate over the array, and for each student, we would print this is, and then the name of the student. And also, I think we had another stupid lambda function here, which again takes a student and just prints hello. Yeah, we can also try this here. If we run that. Something like that. And now we have two students in the list contained, and in the first call for each, then we print this is Michi and this is Julia, and in the second time we call for each, we then print 2 times hello, yeah, because this is not dependent on the students. Which is nice because now we can write kind of functions that take as parameters, again, functions. Yeah, and we can also create these functions here. Now, maybe we could also think about something like a lambda function. So I create one new one, count students. And count students, it makes sense to also implement this in such a context, because we could say, okay, we iterate over the array, and for each student, we increase the count.
Yeah, I mean, we could call a vector.length, but
would
maybe
be too
you
simple.
only want to count students like where the grade is like a 1 or a 2, so you can think of arbitrary conditions when you only want to count students, and then such a lambda function would make, yeah, very perfectly sense, because if you want to write a function which does that, then maybe you want to then later just change the conditions and pass in different conditions, and this would be a very good use case for lambda.
Mm-hmm. I'm sorry, what do you said? Okay, yeah, what happens, what are those about? Yeah, we will come to that. We will need this now, yeah? Okay, so I'll just have the count students lambda function. Okay, for now, we leave out those. We can take as a parameter a student, return again void, basically. And now we want to increase a count here. Let me clean this up a bit here. So now for each student, we want to increase some counting variable. So if I make this variable here, integer count, set it to 0, and then count plus plus. Okay, this doesn't make too much sense, because now when the function is called for the first time, we set the count to 0, and then increase the count by 1. And when we call the function then for the second student again the count is 0. Okay, so this is, I don't know how to do that.
And then afterwards, after we called for each, how would we get this count then?
So it would be nice if we could write the count maybe here inside of the main function. Then we declare this function here. Then for each student, we just increase the count. And then maybe be able to print the count here.
You need to call it for each.
Aha, yeah, this is right. So maybe we call for for each with the student list and the new lambda function, and then maybe be able to print the count. And now this, I mean, this seems a bit awkward now because the count is now a local variable of the main function, and now we would like this to magically appear here inside of the lambda function, which is some other function which is not related to the main function. So how can we do that? And now it's your point, we need now the brackets here.
It allows to see the count from the local function.
Genau. So if, genau. Yes, true. So if we write here count, and let's don't do it with the plus plus. If we write here count, then this function here has access to the count variable. So I would just print count maybe. Here, just print it. And if we run this now, so it seems like it should compile. Compiles, okay, the count is 0. And we can actually print now inside of another function the count of the main function. It's 0, and we never increased it. So this works. Now, what is the problem is, if we, for example, want to do something like this, I write it now very explicitly, count plus 1 is possible, but we cannot assign it, because, okay, it already says it, expression must be a modifiable value.
Yeah, so the value on the left must be modifiable, but apparently our count is constant in this lambda function.
No, this doesn't work. Now there's one thing where we can make it modifiable within the lambda function. I think we need to write it here. We can write here the keyword mutable. And with mutable, well, it seems very nice. However, the count is 0 at the end. What is now the problem? If we just write mutable and just take the count as before, then the count is like a parameter by call by value. So the count gets copied to this function. And if we increase the count by 1, then the copy will be increased by 1 inside of the lambda function. So we will always count 0 plus 1 in each iteration. We will throw away the 1 again, and the next time the function is called, we again have 0 copied to this function, increase it by 1. So again, 1 and throw it away. So we'll never touch this value. It's just always copied. And the solution is not this, mutable here, but the solution is that we can also pass it by reference. So I hope it's on the left side. Yeah. So if we pass it by reference, then this is like I put it as a parameter here by reference. And when I increase this count variable, then I also increase the count variable outside.
So why is this called capture? Because our lambda sort of captures the variable of the outer scope and stores it with the function together in a variable. So for example, now in the count students. So the count students itself now has some count because we captured it from the main. And again, like a function call, we can do this by reference or by value. And if you do it by value and then change it, of course, this won't affect the count in the main because we copied it somehow into the count students and stored it with the count students there. But if we capture it by reference, now we just have a reference to the count and this function stored in this count students variable. Now we can actually change it.
Now let's see whether this really works. And yeah, now the count becomes 2 because it's now really the same variable always. Mm-hmm.
But if we, for example, said that it's not a void function, it's an integer function, then we could just return a count as in any ordinary function.
Okay, yeah. So if we would write integer here,
and we could say int count is as we assign the return value of this function.
so return count plus 1, for example, because we count upwards. And where does this return value now appear? If we return something in this lambda function, we get the return value where we call the lambda function. So we would get here the return value.
Yeah. So it would of course be possible, but now we would need to change our for each function to actually store this return value and then return the last one somehow.
Actually, the returning from lambda function is actually something that is often used, for example, in mapping function, when you want to have for every student where we go through, you want to change something from the student and return as the object, so that it can then be incorporated in a new list that you want to return. There it would happen, but often in functions for each, for example, in languages Java, the for each, or in JavaScript, the for each does not return something. So the lambda functions usually return void. Often, if it's a dynamically typed language, it does not care what it returns as long as whatever happens inside the step. But it's a good point that you brought up, because it's something that happens often with lambda functions that you actually need to do. Yeah,
Yes, of course, the return value does make sense sometimes, just not in this case, maybe because it's a bit weird to work with it if you want to count something. But of course, there are applications where we need to use the return type of some lambda functions, which we'll see next time.
Yeah, so it basically depends on the use case. And now to make it a bit more useful now, so move it back, so we just increase the count. But we could also say, and make it now useful, why should we use that? For example, now I could check if the student get name, for example, equals Julia, and then we can increase the count. So we only, so we basically only count all students that start with the name Julia. And now it makes sense to have such a construction, because now I can also create maybe a lambda function count students too. Just copy it maybe. Which counts all students that have the name Michi. Maybe we should set the count first to 0 again. And now we've always, it really doesn't matter what the condition here is. We just implement the conditions here inside of the lambda function and pass then the function to this for each, and the for each always works the same.
Yeah.
If we wouldn't do it this way, then for each of these use cases, we would need to write a new for each function. A new for each count students with name Julia, we would also need to write the for each. But with this thing, we only need to pass the condition.
Yeah, or if you think more abstract, if you have like a function count students, and then you want to count only with a specific name or only with a specific matriculation number, like when they register to a course or what grade they have, then you need to add more and more functions or more and more parameters that specify what students we want to count. But we could also just accept a lambda, which is always executed, which then returns true or false if we want to count that student or not. So this lambda allows us to pass around these complex conditions more easily.
So, for example, if you have an array of arguments, it would make much more sense to have one for each function and then have separate lambda functions, for example, removing white spaces or maybe formatting them in another way, and you can just find that in a for each function, having each member, each student in the vector.
I'm not sure if we get it. We got it correctly now.
Do we what do you mean?
Let's say we have input string from the user, but it's unformatted, it has some redundant white spaces, but we sort it all in, we just store it all as separate words. Let's say the delimiter is a white space, and we just contain it all into a vector. So we can have multiple lambda functions first, let's say it removes the members that are empty, that are just white spaces, don't have any alphanumerical characters, and then we also have a lambda function that removes semi-redundant white spaces from the strings that have alphanumeric characters. Then we can have those different two lambda functions, but the same for each function in which we execute those functions.
Yeah, so I mean, basically, yes, this is possible. I mean, one limitation is there. If we do with this for each, then I mean, the vector, the length of the vector cannot be changed. But if in each element of the vector there is a string, and then you maybe say, okay, I want to make it uppercase, or inside of the string, I would like to remove certain spaces, then this works. But
Yeah.
you cannot change the number of strings, for example, in this for each.
Yeah, you could, for example, write yourself a function which accepts a lambda, and if this lambda returns true for an element, then you remove it, or else you keep it. And like this, you can pass in many different lambdas. Yeah, I think we should.
Yeah, we should. You can ask your questions later then, and we should then stop.
Yeah, maybe just as a spoiler for next time, if these captures didn't make that much sense, then next time I'll kind of implement it on our own, how such a lambda function can look like, and maybe you then also understand how these captures work a bit more.
Break until 5 minutes, or 5:35 the lecture will start. And thank you, and hope to see you next time, where we really present a few more interesting topics which are beyond the lecture. Yeah, so please come here. There's only like 15 people here or 10 people here. We would really enjoy if you would be here next time as well, because it's like our favorite lecture, where we talk about really new stuff which we also haven't worked with that much, and can present it to you. So it's, I think, really nice. Thank you.